who is a PhD student of Professor Yongping Chang in Shanghai University. He's visiting Professor Vladimir Golotov in Lisbon University right now. So he's visiting us and will give his talk today on Wannier orbital in sphere-orbit coupled Bose-Einstein convection lattices with flat band. So, yeah, very much.
Okay, thanks. This is our written work about the Wannier solitons in a special system with a flat band. Okay. Okay, this is the outline. I will introduce something about the band theory, gap solitons, and flat bands, and about our Wannier soliton and Wannier breathers, and our new work, maybe some basic idea. Okay, let's start. I heard you are most research about the quantum computer. So maybe some basic idea. First, maybe let's consider 1D Hamiltonian, only including the kinetic term and the periodic lattice. Something like this one in the real space. Okay, we know that if in the absence of the lattice only consider the kinetic term, the system always persists the translation symmetry and the momentum k is a good quantum number. So the ground state would be the plane wave and indicated by labeled by the k. In our system, we need to consider the presence of the lattice. So the system is no longer translation environment, but it still maintains a discrete translation symmetry. So now the quantum momentum k is still a good quantum number. And the eigenstate would be the broad wave and labeled by the k with the periodic function. Okay. If you solve this broad wave, and you will finally find the band, which is the energy of the broad state, with the bandwidth and the band gap here. In optical lattice systems, we always have a lot of things to research, maybe like gap solitons. The gap soliton is here is the picture. You can see when we try to construct a soliton here, we need both no interaction and both the kinetic term with the interaction. So let me see. Okay, I ignore it. Sorry. Why we call this gap solitons? Because the energy, the chemical potential of the solitons lie in the gap here. Always be that between the gap. Oh, this one is the gap, this one is the gap, and this solid line is the gap soliton. And the red and the green dashed line is for the broad states. And what we want to do is something like, in a common situation, families of gap solitons bifurcate from the edge of a linear band, maybe here, bifurcate from here to another band. So this line is the whole family of this gap soliton. Okay, when the soliton amplitude tends to 0 here, finally it would transfer into a linear mode of the band. So we know that the basic ground state would be the broad state, which is the extended state, but this one is the localized state. So finally, the Wannier would infinitely increase approaching the block state from which it bifurcates. However, if we consider flat bands, which means the band is complete flat, which is independent of the constant momentum k, which would lead to a localized energy states, eigenstates. I think maybe okay. Let me give you some example here. Maybe this one is 2D dice lattice, and here is the gap. You can see gap, and here is the flat band. Only this one is very, very flat, complete flat. And the block states would be this one, is localized. And also this Kagome lattice here is a different system, and here you can see is also a constant. And also this one is diamond later and by yes here. Okay, so we have a open question that if and how solitons may bifurcate from such a flat band linear models, since now our eigenstate is a localized state, and also soliton is another localized state, right? So you can see this blue line is a family of the gap zone here. This one is chemical potential. This one is the normal, I mean you can see power. And you can see this blue line is a straight line, which means the mu can be potential mu is proportion to the normal, which actually means that the soliton keeps shape between these lines. Okay, valid. Right, this part is normal, and this part should also be normal square, and this must come from the interaction term, which is right, and this keep on change, right? So this is a special properties of this system. So from the other side, if you find such a line, which means this system should be a flat band. However, flat bands in the continuous periodic system were studied mainly in the tight binding limits, which also means the discrete lattice. So our motivation is that what would happen if we consider the flat bands in a continuous periodic system, or you can say 4GP equation. So first, we try to find the flat bands in a continuum model, which we chose to be spin orbit coupling, bosons, and condensates. The existence of the perfectly flat bands in continuous system is impossible. We can find it, but only nearly flat bands can be found. So we need to find the concept of flatness itself. Well, here is the Hamiltonian. This part the kinetic term, this part the optical lattice, this part you can say the spin, this is the orbital momentum. So it's the spin orbital coupling term here. And okay, maybe you have a question that why this system have flat bands. So if you drop this optical lattice here, just drop it, and this Hamiltonian can be calculate the the linear dispersion here. It's very easy. So you can find the chemical potential for the lower branch here. Is proportion to the k to the fourth power. So technically it can be quite flat, right? Because the power is full. So we define the fineness, which is maximal of the chemical potential minus minimum. You can see here a case is quite flat, but it's not exactly flat. So in our system, we define that a nearly flat band should be less than 10 to the minus power 4. Minus.
But experimentally, they use adiabatic capacity to prepare the flat band.
You mean
how to prepare this experiment?
No. As we know that in experiments, no one can find a flat band in this system now, for now.
So it's my question. How can you find how is the parameter regime that you can find the flat band?
Okay, just try. You can try different parameters, and finally you can find it along this condition. Around this condition, you can find it. And you calculate this flatness, and you find the maximal. Yeah, that's it.
Okay, so this big orbit coupling is very weak.
From here, you can see it's actually wish it to be. If you want this flatness to be very small, that means omega should be very big, right?
Yeah, Rabi
should be very big.
is very strong.
Yes. But in experiments, we can't use a very big omega. So that's a reason why we only use this 10 to the minus fourth power. Technically, if you increase the omega here, it can go to infinity, the flatness. But it's impossible in this experiment, so we chose this number. Okay, next we find the gap soliton in this system is older research, so nothing changed. However, the results is different if we consider a special gamma and omega make the system with a flat band. And maybe you can see here is the dots. And we compare the gap soliton with the linear Wannier functions here. You can see they are almost the same. So we think that maybe the flat band, the gap solitons with the flat band should bifurcate from the Wannier functions. So we do another calculation. This is the projection of the Wannier solitons on the Wannier function. You can see it's almost 1 when the interaction is very, very small. Okay? Okay, in this figure, because we can't find the complete flat band, so finally would go to the gap soliton would go to the broad states. Right. Okay. Since we have these results, we think maybe we can construct a theory to describe all these things with the Wannier function, because the Wannier function is a well-defined basis. And here is the two-component Wannier function here. And if we apply Hamiltonian to the Wannier function, and we find that it's almost the eigenstates, but we know it's different. So we have one more term here. Okay, maybe I have. wait. Here is some detail. If you apply a Hamiltonian here, you need to divide this chemical potential into a phi term and another other term here. And if we consider nearly flat band, so this term will be very, very small, which means the Wannier function is almost the appreciably we can say the eigenstates, but it's not. Okay, with this condition, and we are looking for a special solution, which is in the form of the mixed expansion, which is Wannier function for the lowest band and the Borel function for all other bands, which is one you can say the most part is the Wannier function, and it still should contain some other parts. We don't know, so we use, but we don't know, but we think it should be a small part, so we use the epsilon here. It's a small number. And this part should be contain something like Wannier function and Borel function, and with A, B, B be the amplitude here. And if you substituting this expansion into the GP equation and the projection on the Wannier functions, and you can finally find this very complete equations here. Okay, as we say, this f function should be very small. It depends on the flatness. So we think this part can be dropped compared into this mean part here. So finally, we have this function, these equations. It would be this equations, which tell us the chemical potential of the soliton with the normal n here. It should be the line with the circle. And you can compare this line with the numerical results. It's almost the same, right? Okay, one more thing here. We also researched the symmetry here. Okay, it is not so important here, so maybe just skip it. The results that we found that if this soliton with higher, with fully symmetry, would appear to be stable. Yes, right. If this soliton obey maybe only one symmetry, it would appear to be unstable. And one more thing is that we know that the Wannier soliton family is fabricated from the Wannier function. It's very important to our next research, next work. Okay. So we think that if now we have the theoretical function of our soliton, so we can do some new research here. We construct the Wannier bases, which is maybe maybe 3 solitons together. And if we, okay, maybe here. Yeah, here, and with the different phase, or maybe with different normal, we can find the Wannier bases here, you can see. But if you increase the population imbalance, it finally leads to the self-trapping. And when we find this finger, we think we can should have a theory to describe all these things, or maybe explain these things. So go back, we have this answers. Use Wannier function to do all these things. In terms of phase difference with the phi and the fractions of the total number of atoms, which actually yes is n for the different component, you can say, yeah, and put it back to the GP equation. You can find this two, yeah, it's 4 equations, and go under the corresponding Hamiltonian here. And if you plot this Hamiltonian with different phi and n, you can have this finger, phi and z is c, yes. The face portraits here, you can say it should be 2 different faces here. One is maybe like circle, another one is just a line. If it is a circle, you can say the soliton will along this circle. So finally, this particle number would oscillation, just like this one. If the parameters will go to this part, and the particle imbalance always keep almost unchanged, just unchanged. Just like this one you can see, n is almost unchanged here. Okay, so we named this part we call it Josephson oscillations, oscillations around z equals 0. And this part we call it self-trapping, because you can see this part is always trapped here. And let me see. Yes. And one more thing here, you can see here, very interesting result that in our system, it always depends on the interaction strength. If G equals 0, H Hamiltonian would also equal 0. Nothing happens. So we plot another finger. You can say, this finger, we change the interaction, and here is the period. This one, period. And you can say if interaction go to 0, the period will go to infinity. So there is no oscillation anymore. And if you change the z from here to here, it would go through go through 2 different phases. You can say the period will change here and go back 2 different phases. And this dashed line is from the numerical results from the GP equation, and the solid line is from our theory. You can see it's very good. However, you can see here is some difference here. This is because we can consider different interaction, maybe attractive or repulsive. So it would be a little different. Okay.
I have 2 questions. One question is to go back to your Bosonic function junction. So when you consider this soliton ansatz, what will make the difference from the original one? For instance, in Ray Wang Li papers, Ray Wang in Taiwan, he once considered the bright soliton in the Bosonic junction, and somehow he can modify this coefficient Chi1 to derive the new dynamics for this 2 mode. But I didn't see any difference from your calculation. For instance, when you choose this soliton.
Yes. I didn't read that paper, but I think maybe just we can find the bridge here, so we do these things. And
for instance, this H -2 Chi1 square 1 z. This is the normal. No, the other one.
This one? Yeah, right.
This is the normal Bosonic
JJ
model.
Yes.
So I wonder what's the difference?
Yeah, the difference here.
Your soliton model.
Yeah, difference here. I say.
Coefficient is different.
Yes.
Chi1.
Yes, it's different. It depends on the interaction.
Okay, that's my
yes.
Yes.
The normal is this part is nothing here.
Okay. Yeah. Because Gonzalo also work a lot
Yeah,
on
yeah,
this
yeah, yeah.
shortcut. They use this design the shortcut for the spin screens and other things. So yeah, makes sense. Okay,
Yes.
that's my question. So you modify the child one.
Yes. And one more question?
The other question about for the next page. So I wonder, okay, once you have this face diagram,
Yes. This one?
Can you change the interaction from one point to the other point by considering the modulation?
I don't know.
For instance, I have the one state
Maybe.
located at one point, and I want to take the state from one point to the other one.
You may maybe skip from here to here?
Yes. You haven't seen.
I don't know.
Okay. That's not easy.
Yes, maybe you need to add some more things here.
It also depends on the lineage.
Okay. Okay. When we have this result, we think maybe we can use tunnel to transfer the soliton here. So we think maybe we can do more things about the transfer soliton. And okay. Assume that atoms are in this lower state, and if we want to transfer these populations from here to here, maybe the simple way we can just use a light here, and with the special frequency, right? And however, we find that the stimulated emission dominates the spontaneous emission. So it finally would go like this things. You have one light and two lights out. So finally, you can have the transfer efficiency like just 15%. So we think maybe we can use another different light that would lead to the Rabi model. And finally, we know that the probability of the final state will be this solid oscillation lines. You may think if we want the 100% transfer efficiency, you can choose a special time here. Just stop here. However, in the experiment, you can't do these things because the omega here, it depends on the parameters of the different sub-level. So this is impossible. Okay, so we have another different way we call stirrup here, which is, okay, I didn't write it. It means stimulated. Yeah. Raman adiabatic passage. I didn't write it here. Okay, it's something we need another state here, state 2. And we want to transfer the population from the state 1 to the 3 through an intermediate state 2 here. And if you use two special lights, which is maybe light P, light S, and you can finally find a special Hamiltonian here, only with omega P, omega S, and the detuning here. This is important, so just leave it. And if you calculate the eigenstates and eigenvalue, you can find that here is a special dark state. And here is the eigenstates. You can see here we don't have the state 2, right? So that means if we impose the system on this dressed states and change the theta, automatically involve the system from the state 1 to state 3, which is this line, theta from 0 to half of pi, right? it can change from state 1 and to state 3. Right? Yes. So we want to apply this stirrup to our systems. Okay, here you can see, here is one soliton, here is another soliton. We want to transfer the soliton A1, yes, A1 to the another soliton A2, and through a block state. And since that we know that the solitons is our eigenstates, block states is also our eigenstates. So this satisfies that the paired state A1, 2, 3 should be the eigenstates. Okay, and so we use this special ansatz, only include this A1 and A2 to Wannier function and block function here. No, block states here, and with different chemical potential, because we need to satisfy this state level, energy level. Okay, if you use this ansatz and substituting this ansatz go back into the GP equation, you will finally also find this three-modal equation.
But here, why you don't transfer the solid from one state to the other directly? Why you need this blocker as an intermediate step?
Yes.
Because you can already also Lavi oscillation.
Yes.
But why you need still? Sorry.
Yeah, and I understand that. Because we know that a solid transfer only can be achieved maybe by the super lattice, just you guys did. And as I know, we didn't find another way to do these things. Only depend on the tunnel. So we think maybe we can use a special way without a tunnel, just from here to here. Sorry?
You can transfer one by one.
Yes. Yes. Yeah, of course. That's a tunnel. Yes, that's a normal thing.
Yeah. For instance,
just one by one.
Join to the double wave using tension.
Yes.
But
Well, here is in resonance. You have the tuning.
Sorry?
Why you don't have the tuning?
Oh, you mean this part, right? Because the soliton, they have the same energy.
they have seen that.
Yes, they have same energy. They don't have detuning.
You can tune it.
Yeah, of course.
So omega p equals to omega s here. Go back to one slide. So if they, that means 1 and 3 have same energy.
Yes, in our system, yes.
Omega p and omega s should be the same.
Wait, which one?
Omega p.
Omega p? Omega s?
Should be same.
Not necessary.
No.
But if you have
You can address the omega p and omega s.
if you have the tuning, then you use the same omega. Is it possible that you can transfer from 1 to 3 directly?
However, the detuning here is not important. If you have detuning, yes, everything is the same. So it's important, but in our system, we just with the same chemical potential, so we don't have detuning.
You can design your detuning and keep this omega, then transfer it directly from 1 to 3. Is it possible?
I think so.
I don't know.
Previous slide you have like say only 1 and 3 moments.
Sorry?
The previous slide, one of the states is let's call it an state.
Yes, it's zero.
So it goes from 1 to 3.
Yes.
3 without passing 2.
Yes.
So transfer complete.
Yes, we don't need state 2. Mm-hmm.
Why are you using state 2? That's the question.
We need it, but we do not use it.
This is the mechanism of skill.
Yeah.
Yeah, because the skill will assign a quantum property process. It's not like you transform 1 to 2 to 3 and just like the opposite.
Mm-hmm.
Invented in 1985 in Kaiserslautern.
And finally, we find we can do these things. Numerically, you say it's maybe almost 18%. Yeah, I think it's already good. And yes, yes. One more interesting is that the distance here is not important, so we can choose this distance casually, right? Maybe we think that maybe we can try theoretically we can try maybe infinity distance from the theory side. Yes, we can do this, but in the experiment we can do this because the lifetime of the BEC is limited. So maybe. Mm-hmm.
On the other thing is that when you look at this 3 times 3 matrix, you don't have a linear. Your linear interaction disappears.
Yes, we don't need it.
Why? You simply ignore or?
Yes, when we consider the interaction, the Hamiltonian would be very
complicated.
Yes, and also it maybe may don't have the dark states. We can't find dark states.
I can solve this problem.
Okay. So.
Maybe ask us on the distance.
Mm-hmm.
Like you would be limited by the wavelength of whatever light or however you're setting up the stirrup, right? There'll be some wavelength associated or size, right? So the like stirrup usually has laser light coming in.
Yes.
But that has a certain wavelength, right? A certain width. So like your distance here couldn't be arbitrarily small or large, right? Or could it? Is that what you're saying?
You mean
X, the distance is 8 pi over.
Yes.
So you're saying that 8 pi could go to infinity.
In theoretically we can do these things, but
Okay. So like you need an infinite.
We try maybe like 20 periods.
Okay.
And if it's longer, we can do this in numerical calculation in an infinity space.
Like this is an adiabatic limit, right?
Yes.
So like for a finite time, you're going to get some population in state 2, right? So like if you do stirrup over a finite time, you get some thing in state 2. Like at the end, you're in state 3 perfectly, we can get some population there. Does that have any effect? Does that cause a lot of destruction of the transfer? Like, is there, because of this other stuff happening in the background, this non-linear stuff? Or did you just take long times and didn't worry about short times? So when you did this transfer, was it over a long time? Or?
Very long time. Okay, I didn't see this maybe like 8,000. Because you want, if you transfer from state 1 to state 3, it should ensure the diabatic evolution. So it requires a very, very long time. And also in our systems, the intermediate states would be the broad states. If you maybe extend maybe a few part of the broad states, it would escape a lot of atoms. So we need a very, very long time to ensure the diabatically involved. Yeah, that's all. Yes. One more thing, we need this soliton be the eigenstates. So we consider the system with a very, very weak interaction so that we can use the Wannier function. So if we use a very, very weak interaction, only flat band can confine the solitons. Yeah, maybe you can take this finger. If you, here the flatness, if you for the normal band, you can say finally the soliton is just approach the closed state. This is the inverse participation. That means the localized or delocalized. So here it means is delocalized. Then the state would be the maybe something like closed state. Closed state don't need to transfer. It's already expanded state, right? But we try to transform a localized state to another defined position. So we need to spin our copy, or you can say we need a flat band to confine the solitons, confine the atoms here. Yes.
Okay, and then we try to tune the interaction. It can also do the same from.
If you yes, on the other hand, if you use maybe very high interaction, you don't need that spin over copy, you can confine the soliton here. Yes, someone did that. However, if you consider normal band, we don't have this theory here. You don't know if we have dark states or not. So as I know, if you use the normal soliton, you can do this because you don't have dark states.
And maybe you can tune this spin coupling, then change the dynamics of what she mentioned.
Maybe. Actually, the important thing here is how to cut the soliton, and the blow states. This key is very difficult to design. Very difficult to design coupling strength, coupling term. We use a lot of time to design this omega to do these things. Yes.
I remember you have a plot component.
Yeah.
So here in your system, why you choose this kind of?
Yeah, it's another paper about the flat band and gamma soliton. So it's a 2D system, and they finally find the gamma soliton with the flat band in a discrete lattice. It would with zero power threefold. It's a very special results. If you know all these things in a normal band, if you consider the behavior here, it would maybe start from here. N cannot be zero. However, if you have a flat band, you can be zero, exactly zero. I think this means that because in a normal band, you need the interaction to confine the solitons, right? The attractive interaction to confine the soliton. So if the power, you mean the number, is too small, then the interaction is also too small. So you can't find the soliton, localized soliton. So when we see this paper, we think maybe we can do something in a continuous systems. It's our motivation.
Any other questions? If not, let us end